Convolutional neural networks learn by observing multiple samples of various objects. During the training phase, a network develops an internal representation of each of the classes that enables detecting samples of this class in the future. But what are these representations, and how does the network characterize the objects using them? BLOX is designed to help answer these questions using visualization to reduce the trial and error when designing deep networks. Our main observation about convolutional neural networks is that they learn in a hierarchy of similar classes. Understanding and exploiting this hierarchy is key to introducing targeted refinements to the network architecture, which yield significant improvement in accuracy. This video illustrates the power of BLOX through the example of image classification on ImageNet dataset. Let us observe the confusion matrix between 1000 class categories. There are two major blocks that represent natural objects and artifacts. Let us divide these blocks recursively. The subblocks represent fine-grained groups of similar objects such as dogs, birds, and vehicles. The corresponding hierarchy of similar classes can be explored at multiple levels via the hierarchy viewer. This viewer can provide information about each group in the hierarchy, such as group-wise classification accuracy. This confirms the hierarchical structure of the error, as the majority of confusions occur within increasingly narrower groups. The hierarchical structure of classes are also reflected in the feature detectors inside the network. In this view, each column represents a feature detector and displays in color how its responses vary between different classes. For example, certain detectors respond mainly to animals. Of these detectors, some respond mainly to mammals, birds, or invertebrates. These detectors learn common features between the respective classes such as shape, texture, and pose. Other detectors respond mainly to artifacts. The separability between these groups can be traced back to earlier layers of the network, whose feature detectors can already distinguish between high-level groups. Let us inspect the features developed at an advanced layer to recognize strawberries. For this purpose, we sort the feature detectors by their response level among strawberries. Let us see what are the most relevant features of strawberries the detectors are looking at when scanning an image. The most dominant detector is looking for red objects. By inspecting the class hierarchy, we find that this feature is also activated among many classes, especially vehicles and fruits. The other dominant detector is looking for dotted objects. We can verify this by checking the activation maps of the corresponding images. These maps highlight parts of the image that activate the selected feature detector. Strawberries that did not have these features were not detected correctly by the network. Now we will illustrate how we can improve the performance of CNNs based on the insights that we gain from using BLOX. Let us observe how the error structure evolved during the training. Initially, the model is random, resulting in a uniform distribution of the values in the confusion matrix. In the second epoch, the separation between high-level groups improves and subgroups within them emerge. In the final epoch, the CNN makes fewer overall confusions that are generally limited to narrow groups. Our findings about group separability and model convergence enable us to improve training speed and accuracy by involving the hierarchy information in the design and training of CNNs. Specifically, we built on top of the AlexNet and created branches that performed group-level classification. For each layer, we selected groups that we identified as most separable using the corresponding feature detectors, and designed a loss function to enforce the separability. In this example, we require the first layer to classify the samples into 3 broad groups only, and increase the number of groups in subsequent layers. Through evaluations, we show that our hierarchy-aware CNN reduces the top 1 error by 20% and the top 5 error by 30%. We also briefly demonstrate how BLOX can support inspection of the training data quality. Let us filter out confusions that are resolved among the top 10 guesses and focus further on incorrect classifications despite high prediction scores. Many of these samples did contain the predicted object beside the other ones, or were even mislabeled in the original dataset. The observations can help the user on better understanding of the cause and errors, as well as the curation of more accurate training data.